Good evening, Chester. A pleasure to be back to talk to you once again. This time about the mission Gaia. As you can see there, a 5-year mission to map 1 billion stars. It did that so well, they changed its mission to a 10-year mission to map 2 billion stars. Fair enough. So what am I talking about? Why map the stars in the Milky Way? How can they be mapped accurately? What type of data do we get? And what can we learn from all the data that has been and will be coming from the Gaia mission? So let's start with why. Why do we map the stars at all? It's not simply a question of saying, well, we want to know where the stars are so that when we map them out, we can find objects again at a later date, or we can tell if things have moved, or we can tell if any new objects have appeared. Yes, that might be why we make star atlases, but it's not Gaia's mission. Gaia's mission was to determine the positions of stars extremely accurately with a precision that's high enough that we can get a full 3-dimensional map of all of the stars in the Milky Way. Well, technically not all of them, but a large enough fraction of stars that we can get a pretty good idea of what the Milky Way is actually doing in terms of its history, its future, and ultimately its evolution and its dynamics. So how do we map the sky? Is it simply a question of photographing the sky and stitching all the images together? No. Number one problem with that is everything is motion. We don't really think of the stars in motion. Yes, they appear to move because of the Earth's rotation, but here we're talking about them moving on the background tapestry of the sky. From day to day, we don't notice that much in way of movement, but Gaia has got sufficient precision that it can actually map the tiny motions of the stars. And basically, the entire galaxy is in motion, and therefore, if we want to know what the stars are doing, we've got to worry about the fact that everything up there is in motion. The second problem is it's not just a question of taking snapshots of the sky because stars are at different distances. We're used to the idea, I guess, that although we see, for instance, Orion as a constellation, a particular pattern of stars in the sky, all of the stars of Orion are at different distances. And so although in principle we can take a picture of the constellations easily enough, if we want the full 3-dimensional picture, we've got to worry about the distances to the stars. And in essence, most of what I'm saying this evening is about how do we determine distances accurately enough to get a full 3-dimensional model. Now, if we think about not only the fact that we want distances because we want the 3 dimensions, we also need the distances if we want to understand simply the stars themselves, let alone how they actually behave in the dynamics of the Milky Way. Perhaps you're familiar with this idea of a color magnitude diagram or a Hertzsprung-Russell diagram with luminosity on the vertical scale and color of a star on the horizontal scale. But if we don't know the distance to a star, we can't work out its luminosity. How do we know if it's a bright star a long way away or a dim star relatively close to us? If we don't know the distance, we can't work out what type of star we're dealing with. For instance, if we happen to be looking at a blue star, how do we know if that blue star is a supergiant or a main sequence or a white dwarf? Or if we're looking at something that appears to be a red star, how do we know whether it's a supergiant or a red giant or a red dwarf? Yes, we can get some hints from the spectrum of the star, but really we need to know the distance so that we can say that's its apparent magnitude. If we know its distance, then we know its actual or absolute magnitude, or if you prefer, its luminosity. And then we know what type of star we're dealing with. Bear in mind that if we actually don't know what type of star we're dealing with whenever we look out into the galaxy, well, actually, we have very little information about any planets that might be going around that star. Remember how we find exoplanets? We either look for the transit method, which means a planet will pass in front of the star, and the size of the planet will determine how much light is dropped from the star. But strictly, it's the size of the planet relative to the size of the star that determines the amount of dip in a transit. And similarly, if we're looking at the spectrum of a star to see it wobble by using the Doppler shift, then we determine not the mass of the planet, but the mass of the planet relative to its host star. So if we don't know the size of the star and we don't know the mass of the star, then actually we know very little about any of the exoplanets that are going around them. So we really do need distance to know about the stars themselves, and that gives us information about stellar evolution, and to give us that three-dimensional coordinate which allows us to work out where the stars are, and if we watch them for a few years, how they're moving, and then we get the full dynamics of the Milky Way. So perhaps you're all familiar with this idea of parallax. That's how we determine distance. You've probably seen this before. If you hold up a finger and blink your eyes, your finger appears to move relative to background objects because your finger is closer than the background objects. And that's how it's often presented in a diagram like this. A nearby star will appear to change its position relative to fixed stars in the background as the Earth goes round the Sun. So we have a baseline to this triangle that allows us to say, if we know how much a star appears to shift as the Earth goes round the Sun, given that we know the distance from the Earth to the Sun, by geometry we can work out how far it is to the nearby star. But diagrams like this are always very misleading for two reasons. One is they always talk about the motion of a nearby star relative to fixed stars. There are no such thing as fixed stars. Every star in the Milky Way is in motion. Therefore, at the extremes of precision that we're trying to get here, we can't simply say, let's assume the more distant stars are fixed in position, because we know they aren't. Not only that, but when we come to measure this rather tiny angle here, this parallax angle, not only do we have to worry about the fact that how do we measure an angle of one star when we don't actually know what the background is doing, we have to worry about the fact that that angle, the so-called parallax angle, which gives us by geometry the distance, is much, much, much smaller than that diagram would indicate. Remember, we've got the distance from the Earth to the Sun, 1 astronomical unit, but here we've got the Sun to the star as being, well, a similar sort of distance. Whereas in fact, the distance to the stars are millions of times larger than the distance from the Earth to the Sun. So this triangle here, where we're trying to measure that parallax angle to get the distance, it's not a triangle which is about twice as long as it is wide. It actually should be a triangle that's 1,000,000 times longer than it is wide. It is a tiny, tiny angle that we're trying to measure here. If we think about actual distances, a hypothetical star about 3 light years distance would give us a parallax angle of 1 arc-second. I hope you're all familiar with 1 arc-second being 1/60th of an arc-minute, being 1/60th of a degree. Physicists tend to work in radians, but most astronomers work in degrees and arc-minutes and arc-seconds. So a star 3 light years away would have an angle of 1 second, which is why we call that distance 1 parallax second, or 1 parsec for short. So 1 parsec is the distance at which a star would subtend a parallax angle of 1 second. And a parsec works out to be, when we think about the geometry and actually work out the numbers, the difference between light years and astronomical units, etc., it turns out that 1 parsec is just over 3 light years. The nearest star is 4 light years, which means it has a parallax angle that's even smaller than that. So all stars which are more distant than 4 light years, more distant than 1 parsec, will have parallax angles of a fraction of a parsec. And a star that's 10 or 100 or 1,000 light years away will have a parallax angle of 1 arc-second or 1/10th of an arc-second or 100th of an arc-second. The further the star, the smaller the parallax angle will be, because we've got a fixed baseline here of Earth to Sun distance. So there's the crux of the problem. We want distances because we want to know about stars and we want to know about 3-dimensional coordinates to get the entire Milky Way. So distances are critical, and for distances we need parallax. But for parallax, we really need to know about the angle that we saw in that triangle, but we haven't got fixed stars in the background. We can't simply work out a star's motion relative to some other star because we don't know that distance either. It's a chicken and egg problem. We want to know the distances to the stars. We need a fixed frame of reference. All the stars themselves are in motion. So we've got this really tangled problem of the stars are in motion and the Earth is in motion, and we want to disentangle these two things so that we can work out what the stars are doing and get their distances from the parallax angle. That's why mapping the stars in the Milky Way is not a trivial task. That's why, in a sense, we had to let the technology catch up with the ability to measure tiny angles before we were able to map out the stars in the Milky Way to the precision that we really want to do. So how do we go about mapping them accurately? So that's the problem. Untangle these two separate things, the apparent motion because of the motion of the Earth and the actual motion of the stars. We need two critical things. We need high precision. Maybe that should be really very, very high precision. And we need a fixed coordinate system. And we need high precision because the parallax angles are so small. As soon as we go to tens or hundreds or thousands of light years away, we're talking about really, really small angles. So we need high precision. And we need a fixed coordinate system because the Earth is in motion, which gives us the parallax, and the stars are in motion. And those two motions get tangled together. Just as a little aside, this is not particularly relevant, but historically it's interesting. Back in the 1980s, somebody said, why do we limit ourselves to the Earth-Sun distance for the base of this very narrow triangle? Why don't we make the baseline bigger by having a spacecraft take some of the measurements 1,000 AU away? Why don't we take a spacecraft and fly it out into the distant part of the solar system? Then our baseline is not 1 astronomical unit, Earth-Sun, but 1,000 astronomical units. Great, make the angles 1,000 times bigger rather than try and make even more precise measurements. This was thought about in the 1980s, but with the technology available at the time, if you had an ion drive to get you out to the outer solar system, it was calculated it would take about 50 years to get there. So if they had actually done this in the 1980s, it would still be on its way, and it would still be on its way to the outer solar system. So they decided not to actually go with this particular idea. So what coordinate system should we use? We want a coordinate system that's fixed in the sense that it's not this star relative to that star. Well, you could say, well, that's easy. We all know about right ascension and declination. It's the coordinates we see when we look in Norton Star Atlas. That gives us the coordinate of any star in the sky. Right ascension and declination are effectively just extensions of a coordinate system relative to the equator of the Earth and relative to the poles of the Earth. Declination is analogous to latitude, and right ascension, or hour angle, is analogous to longitude. So why is that a problem? Surely they've been good enough for star atlases since the days of the first Astronomer Royal. So why are they not good enough? They're not good enough because right ascension and declination are always changing. They are not a fixed coordinate system. So we look at a page of an atlas and say, well, I can work out the position of any star I like just by saying there's a right ascension line, there's a declination line, so I can read off a particular coordinate. But if we do that, for instance, for Norton Star Atlas, we find Norton Star Atlas 1950, Norton Star Atlas 2000. These are not publication dates. These are epochs. These are the dates at which the coordinates of the stars are given. Because, why is the coordinate always changing? The coordinate is always changing because the Earth is always changing. The Earth's axis is precessing. The pole points to different stars at different times. At the moment, the pole happens to be pointing close to Polaris. Wait a few thousand years, it'll be pointing at a different star, like Vega, for instance. So if your coordinate system is fixed on the Earth, that means your coordinates will change day after day after day. So star atlases tend to be made and published, and coordinates are printed for a particular year. Then they're out of date. And then they're printed for another year, 50 years later. Then they're out of date, etc. So right ascension and declination, not a good idea for precision measurements of star positions. So if the Earth isn't good enough, why don't we measure relative to the Sun? The Earth is going around the Sun, presumably, and therefore the Sun should be a good coordinate to use. Well, no. Even using the Sun would give a small error because the Sun itself is moving. If you look at how the Sun moves because it is effectively counterbalanced by Jupiter and Saturn, and this animation is slowing down just to show you that the center of the solar system actually falls inside the Sun in a few years' time. If we go back a few years, the Sun was quite a long way from the center of the solar system, simply because Jupiter and Saturn happened to be on the same side of the solar system, and so as a sort of counterbalance, the Sun was a little over to one side. So although we tend to think of the planets go round the Sun, that's obviously what we teach kids, actually all the planets and the Sun itself are all orbiting around a common center of mass or a center of gravity. Astrophysicists tend to call it the barycenter. It's effectively the same thing, the center of mass or the center of gravity. So if we know that all of these objects in the solar system are orbiting around the center of mass, let's use the center of mass as a fixed point. And we can work out how the Earth is moving relative to that point easily enough, and we can work out our coordinate system accordingly. So we're going to use the center of the solar system as a reference point. If we imagine what the sky looks like, let's exaggerate it somewhat, but effectively, if we were to look at the sky, all of the stars appear to be moving in circles or perhaps ellipses, depending on which part of the sky we're looking. If a star is moving in a big circle, that means it's fairly close. If a star is moving in a relatively small circle, that means it's more distant. So if we find the size of the circular motion because of parallax, because of the motion of the Earth, knowing the distance from the Earth to the Sun, we can work out the distance to the star simply from geometry and knowing our triangles. But in addition to parallax, stars have proper motion. They have their own motion around the Milky Way. So in fact, every star in the sky is making a motion which is effectively a corkscrew. It's a combination of the circular motion because of the Earth around the Sun, plus the motion of the star itself as it presumably orbits the center of the Milky Way. So it's the sum, if you like, of circular motion as well as linear motion. We can treat it as linear, even though the objects themselves, the stars, are probably orbiting in very big circles or ellipses around the Milky Way. It takes hundreds of millions of years for a star to orbit the Milky Way, and we're only observing these stars for a few years, so we can treat their motion over a few years as essentially a straight line. So we need to disentangle for any star what's its proper motion, the straight line, and what's the size of this circle, the parallax that gives us the distance. If we can accurately determine the position of a star over a few years, following the corkscrew, then we can disentangle the corkscrew and say that's the result of a linear part and a circular part, and those two give us different information. One gives us the distance, the other gives us the motion around the Milky Way. The first satellite that tried to do that was called Hipparchus. There's the acronym there. It's thought that probably they started by paying homage to the Greek astronomer Hipparchus and then thought, what kind of acronym can we make out of his name? And then they came up with this one, High Precision Parallax Collecting Satellite. Back in the 80s and 90s, the job of Hipparchus was to map out something like 100,000 stars, relatively bright stars, magnitude 12 and brighter, and its job was to map out the parallax of these stars to a precision of order 1 milli-arc second. So 0.001 arc second was its nominal precision. And it did that over those years, a few years in the early 1990s. It produced a catalogue, the Hipparchus catalogue, of 100,000 or so stars to that sort of precision. And that catalogue was used for quite a few years, including, for instance, it was one of the first catalogues used by the Hubble Space Telescope. And so that allowed the Hubble Space Telescope to point accurately at the particular object it was interested in, because we now have hundreds of thousands of stars whose position is known relatively accurately. That was the 1990s. Technology moved on, and it was decided we really, really want to know the positions of as many stars as possible to an accuracy even better than milli-arc second. And then we'll be able to see more distant stars in the galaxy, and with higher precision, we can get these distances more accurately. So along comes Gaia in the teenies into the 20s. Let's not worry about the acronym. you can see it for yourself there. The acronym was put together when they thought that they were going to build a satellite that might use interferometry to get the accuracy. In the end, they decided not to use interferometry, and I'll tell you what they did shortly. So the acronym is actually redundant. But they liked the name so much, and they'd already bought the domain, Gaia.com, so they couldn't get rid of that. So they decided to keep the name Gaia, even though it no longer refers to how it actually works. The idea was Gaia was going to improve on Hipparchus by mapping not 100,000, but 1 billion stars, ultimately 2 billion stars. So the number of stars in its catalogue has now gone up by, 10,000-fold. Not only that, but the accuracy with which it was going to work is not milliarc second, but its designated resolution is of order 10 microarc seconds, where of course a microarc second is 1,000th of a milliarc second. So we're talking about 10 millionths of an arc second is its design resolution. And the faintest stars that it could possibly see are something like magnitude 20, a lot fainter than Hipparchus. And because it has much higher precision, that means we can work out parallax angles of much more distant stars. So instead of only looking at the nearby 100,000 stars, Gaia was able to look further out into the galaxy. It's difficult to get your head around what 10 microarc second actually means. You can say, well, I sort of know what an arc second is, and I know what a million means, but trying to visualize what does 10 microarc seconds as an angle actually mean. So let me give you an analogy that gives you an idea of the stupendous precision with which Gaia actually operates. 10 microarc seconds, that many arc seconds if you count the zeros, that's equivalent to the thickness of a human hair seen at a distance of 1,000 kilometers. So one way of thinking of it, imagine you were in Land's End. Imagine you're looking at somebody in John O'Groats. You are trying to determine the position of somebody 1,000 kilometers away, and you're trying to measure their position to an accuracy of the width of a human hair. That's what Gaia was tasked to do. You could ask, okay, that sounds fantastic, but are there no telescopes that will do the job? Doesn't the Hubble Space Telescope have phenomenal accuracy and precision? And what about this new telescope that's coming online now? The Chamonix telescope, previously known as the Large Synoptic Survey Telescope. What about that mapping billions of stars? Well, yes, the Hubble does have some rather high precision. It can certainly get star positions to better than a milliarc second. And the Chamonix telescope can certainly survey billions of stars. That's its job, basically. But they are complementing each other in the sense that the Chamonix telescope doesn't have the resolution. It has a resolution only a fraction of an arc second. And the Hubble Space Telescope does have high precision, but it's only actually worked out the parallax of maybe 1,000 or so stars in its 30-year life. So yes, if you wanted the Chamonix telescope to map the positions of stars over a few billion stars, how long would it take to do that? Well, its design parameters are something like it could map out 10 billion stars in something like 10 years. But if you wanted the Hubble to do it at high precision, in principle, the Hubble has a reasonable resolution. But if you wanted it to map out the parallax of stars, it would take at least 1,000 years, if not 2,000 years, if not 5,000 years to actually get the sort of precision that we want. Nobody thinks that Hubble's gyros are going to last for 2,000 years. Therefore, neither of these telescopes, wonderful though they are up to the job that Gaia was built to do. So how does Gaia achieve this fantastic resolution? It's a European Space Agency mission. I should say was, I suppose, as it's now ended. So it was an ESA mission. A number of different countries contributed. The optics for Gaia were built in Germany, France, Belgium, for instance. The UK built the detector and some of the power systems. All the systems integration was done by a company called Astrium, which is now part of the Airbus consortium. It was put together in the noughties and to the early teenies. It was launched in December 2013 and was on station around L2 a few months later. And this, of course, is the same place that the James Webb Space Telescope now occupies. A reminder that there is L2 on the right-hand side there. That red dot, let's ignore the other red dots for the moment. There's L2, a point in space sitting 1 million miles above midnight. Okay? The noon side of Earth is, of course, on the sun side, so the opposite side is the midnight side, and L2 is hovering 1 million miles above midnight. And that's where Gaia and ultimately James Webb were put into halo orbits. In both cases, they had sun shields, and the idea of a sun shield is it blocks any light from the moon and the Earth and the sun all at the same time. That's the advantage of going to L2. You can block everything with one sun shield. So all of the light sources are out of your way. And the testing was done by, again, by Astrium at their Toulouse factory. And here you can see, testing the sun shield, there's solar panels on the underside, giving it the power. But also this particular animation shows you approximately the scale. You can see the sun shield is something like 10 meters or so in diameter. And Gaia is just a few meters in diameter. So yes, like James Webb, they tested the sun shield, not as complex as James Webb, but they tested the sun shield to make sure everything was working correctly. But again, we're coming back to the question, well, how did it get micro arc second resolution? We know that big mirrors give you better resolution. A small amateur mirror might give you rather poor resolution of only 1 or 2 arc seconds. And you'd need an absolutely huge mirror to get a resolution of 10 micro arc seconds. It would need to be kilometers in diameter. But clearly, from the animation we've just seen, Gaia isn't kilometers in size. So how did it work? Let's just remind ourselves about mirror sizes. Here's a number of mirror sizes to scale. The largest telescope in the world at the moment is Gran Telescopio Canarias, nominally 8 meters diameter. We can't strictly say diameter when it's full of hexagons, but you know what I mean. 10 meters or so across. It's not yet overtaken, but soon to be overtaken by the extremely large telescope. But for the moment, that is still the largest telescope in the world. If we have a look at space telescopes down in the bottom left, they're probably a bit small, so let me make them a little bit larger for you. There's Gaia. It has 2 rectangular mirrors, but notice they are tiny compared to the James Webb. They're not really much bigger than the Hubble Space Telescope, and they're sort of comparable in size to the Kepler Space Telescope. So despite having mirrors of very modest size, how does it get micro arc second resolution? Well, it's a combination of the hardware involved and the way it operates, both of which are rather novel, as you can perhaps tell from the fact that it has 2 rectangular mirrors. Firstly, the hardware. It has a very large detector. The detector is made up of over 100 CCDs. A CCD is a charge-coupled device. This is going to be important for what I say in just a moment. Charge-coupled devices are devices that allow light to hit them. The light is converted to electric charge, and then somehow we have to measure that electric charge because that tells us how much light arrived at any pixel in the array. Gaia has 2 mirrors, and technically it's actually 2 telescopes, although we talk about it being a telescope. It's actually 2 telescopes that are pointing not quite 90 degrees apart, more like 100 and something degrees apart. They are looking at different chunks of sky for a reason I will explain in just a moment. But it's not just the hardware, it's the way the hardware is used that makes Gaia unique. Both telescopes generate images that end up on the same detector. And you might think that is ridiculous. Why on earth have you got this telescope generating images going to a detector, and this telescope, looking at a different patch of sky, is also generating images which are being sent to the same detector at the same time? That might sound crazy, but the reason it works is because Gaia spins. And those telescopes are continuously sweeping out ribbons of sky. Gaia does not take images, despite what you might have thought. You might have seen something that looks like a Gaia image, but no, Gaia is a device for measuring the positions of stars. It does not take snapshots. Gaia, in that respect, is very different from its cousins like the Hubble Space Telescope or the James Webb Space Telescope, which generate wonderful images, and that's one way of getting the public on board, of course, is to publish the various images that are taken by the Hubble or the James Webb. Reading data from the detector is critical to the mode of operation for Gaia and why it's different from the mode of operation of Hubble and James Webb. So it's worth taking just a few minutes to make sure we understand why getting data off the chip, remember, light hits the detectors generate charge, and then we've got to get that charge off the chip and convert it into a whole load of numbers where those numbers tell us how much light arrived here, how much light arrived here, how much light arrived here, etc. Getting from the chip to the numbers is completely different in these different space telescopes. First, a reminder of how it works with Hubble or with James Webb. It's called stare mode because we are basically saying we've got a fixed patch of sky. We're going to try and convert the light from these distant stars into an array of numbers because it's ultimately digital numbers that we want. And it's done in so-called stare mode in the sense that we tell the telescope to stare at a patch of sky and slowly the image builds up. I'm just showing a few pixels here, of course. Second by second by second, the image builds up until the exposure is complete, and then we read out one line at a time and then one pixel at a time what is the amount of charge in each of these pixels. So they are put into a register, and then the register is read out. Pixel by pixel, the amount of charge is measured by an amplifier. Then the next line shuffles down, and again, the pixels are shuffled across, and pixel by pixel, we measure the charge. Then the next line shuffles down, and then pixel by pixel, we measure the charge. It takes about a millisecond for a line to shuffle down. It takes about a microsecond for each pixel to move, get its charge read, and then move on to the next pixel. So it might take, for millions of pixels, it might take a second or two or three to read all of the information from the chip and end up with a collection of numbers. And as long as we know how the chip was read, we can always say for any given number, we can work out which pixel it actually came from. So we can, if we wish, then regenerate the image from the data we've just read. That is so-called stare mode. You either fix your telescope. In the case of amateurs, you drive your equatorial telescope such that it follows the stars, derotates the Earth effectively. For the Hubble or the James Webb in space, you tell them to fixate on one particular point and not budge while the exposure is being taken, regardless of whether that's seconds or minutes or potentially hours, maybe even days in the case of the Hubble Deep Field, for instance. Gaia is different. Gaia is spinning. And if we wanted to take images, well, we can't because Gaia is spinning, which means the images are continually, the image of a star is continuously moving across the detector. If we tried to take a snapshot, we would just get lots of blurred stars. So it works in a different way. Because the entire field is continually in motion, we read the CCD. The CCD, just as before, is read by shifting a line down, shifting down, shifting down. We do that so that the shift of the CCD is exactly in sync with the drift of the stars. So a star drifts downwards at exactly the same speed as the CCD is being read out. And eventually the star reaches the edge of the CCD, at which point, again, the information is read out pixel by pixel. When we find a star, we make a note of the time. There's an onboard atomic clock. We can effectively say, well, now we know the brightness of the star because we've just measured it, and we know exactly when that star hit the edge of the CCD because we've measured that with atomic precision on the timing. I've shown that for one star. In practice, that is happening for multiple stars in the field of view all the time. I'm going to take a break in just a moment, but let me finish by just addressing this point of what's this ridiculous idea of having two telescopes pointing at different patches of sky, but bringing those images to the same detector. Well, actually, you've probably heard of an instrument that does that before. You may not realize it, but that is precisely how sextants work. Now, I'm fairly sure you've all got a sextant in the boot of your car, just in case, sooner or later your GPS is going to fail. So you need one of these in the boot, just in case. How does a sextant actually work? Maybe you haven't used one recently, I don't know, unless you happen to be sailors. But the idea is you have a couple of mirrors such that when you're looking at the distant horizon through this little telescope there, so your eye is looking into the eyepiece and you're seeing the horizon, these two mirrors will reflect either the sun, or let's just assume it's a star. A star will reflect off these two mirrors such that the star appears to be in the same place as the horizon. In other words, you adjust the angle of one of these mirrors with phenomenal accuracy. In the case of a sextant, you can read off the angles very accurately. You bring the star down to the horizon. Even if the boat is swinging backwards and forwards in heavy seas, you've brought the star down to the horizon. So you're seeing the horizon and the star on the same detector, the back of your eye. So even though you might be moving a lot, you can still tell that the star and the horizon are together. So it doesn't matter if they're moving, they are together. The sextant brings the star down to the horizon and puts both in the same position on your retina. So two different objects in the same detector. Okay, in the case of a sextant, it's that angle we want. We read off the angle on the sextant, and that angle allows you to determine your latitude. Longitude is a different question. But the reason I'm showing you the sextant is because it's the same principle. Light from two objects, the horizon and the star, are brought together by mirrors so they appear together on the same detector. That allows you to get the relative angle of the horizon and the star, or in the case of Gaia, that star and that star, because the light from those two stars is brought to the same detector at the same time. So any two stars that are separated by that angle are basically being mapped at the same time. It gives you phenomenal accuracy even over very large angles of sky. And I'll show you how Gaia does that after the tea break. Just before the tea break, I was explaining that this idea of Gaia having two telescopes pointing at different parts of the sky is in principle no different from a sextant, which is trying to bring a star and the horizon to the same point such that one detector can see both at the same time. It gives you a phenomenally accurate way of telling where two objects are, even though they are separated by huge chunks of sky. Let's see how that translates in the way Gaia works. So that's what a naked Gaia looks like. That's Gaia without its shroud. Two telescopes, you can see the sizes down there, about 1.5 meters long, 0.5 meters wide. They are rectangular because we want very high precision in one direction and not so worried in the other direction. The two mirrors are mounted on this hexagonal optical bench, looking like a donut. And that's an idea of how the technicians at Astrium put it together. So again, you get an idea of scale there. So let's have a quick look at the detector on which the two telescopes are sending their images. The center of the detector is made up of a large number of so-called astrometric CCDs. Each of these CCDs is the size shown there, and each CCD has got 9 million pixels, and the pixels are rectangular, narrow in one direction, not so narrow in the other direction. Again, we want very high precision in the horizontal direction, which is why the pixels are relatively narrow. We're not that fussed about the other direction. So this aspect ratio mirrors, if you'll excuse the pun, the shape of the rectangular mirrors. We've got two telescopes sending images to the same set of astrometric chips. So how do we know which star came from which telescope? We really need to know that because we're trying to work out where is this star relative to that star, where is that star relative to that star, etc. So we need to know where the star came from in terms of which telescope. And that's what these two right-hand sets are. They're called sky mappers, and it's arranged such that stars from telescope 1 appear in the right-hand column, but not the left, And stars from telescope 2 appear in the left-hand column, but not the right. So as the stars drift across the CCD array, the sky mappers tell the onboard computer, this star came from telescope 1, this star came from telescope 2, this star came from telescope 1, etc. And it's doing that, of course, all of the time as large numbers of stars drift across the array. After the stars have drifted across the astrometrics arrays, which are designed to do the timing, when does a star reach the edge of a CCD, which we'll see shortly, they also go through, the light goes through prisms such that we measure how blue is the star and how red is the star. So even without a spectrum, we can place stars on the Hertzsprung-Russell diagram. We know how red they are or how blue they are, so we know where they are in terms of the horizontal position on the HR diagram. Some of the stars will then go through a spectroscope and have their full spectrum taken. Not necessarily every star, not the faintest of stars, not every star in the sky, but hundreds of millions of stars will have their spectra taken as well as their colors and their brightnesses. In addition to all of those chips, there's a few chips that are designed to make sure that it stays focused and to make sure those two telescopes are pointing in the directions you think they are. And just to give you an idea of timing, the star drift direction for this detector is right to left, as I've got it mapped out here. And it takes about 4 seconds for a star to drift across one of these CCD modules. So it takes about a minute for the star to drift all the way across. Remember, each of the individual grey rectangles here has got 9 million pixels. So a star might only spend a millisecond or so on any given pixel of any given chip. So let's see how it operates. ESA have produced a rather nice video to give us an idea of how it works in practice. So here we have Gaia and its two telescopes, color-coded, magenta and cyan, just so we can keep track of which one it is we're talking about. So firstly, we're going to have a look at what happens to light that comes in on the cyan telescope. Number 1, it hits number 1 and it is folded, 35-meter focal length is folded until the light finally hits the detector. So the field of view of telescope 1 produces a whole load of stars which appear all over detector 1 and the first sky mapper on the right. Simultaneously, telescope 2 is doing the same thing, and it is producing its image again on the same detector, but this time sky mapper 2 is recording them. And Gaia is spinning, which means the entire set of stars drifts across the CCDs. If we follow one star, its brightness is recorded. When it reaches the end, the time it reaches that point is recorded as well. Then it goes across the next chip. It builds up in brightness, its brightness is recorded, and the time that that star reaches that chip is detected. And so chip after chip after chip, as a star drifts across the whole array, we get lots of repeated brightness measurements as well as timings. And then the star has its blue measured, has its red measured, and if it's in the right position, the star has its spectrum measured. And that is going on across the entire detector. So if we think about what happens in practice, it's not just one star that's being tracked. The system only reads where there's a star. In other words, it knows where each star is because it's mapped out on those first sky mappers. Then it only bothers reading data when it knows there's a star. In this case, this little cartoon has, 20 or so stars drifting across the detector at any given time. In practice, Gaia has, at any given time, 500,000 stars drifting across the detector, and every CCD module is being read out continuously to find all of the stars and the timings of when those stars arrive at the edge of each of the detectors as they drift across. So thousands of stars every second are having their brightness measured and their timings measured with the internal atomic clock. Thousands of stars every second of every day, 24/7, for 10 years. That's how Gaia gets a humongous amount of data by reading continuously over an extended period of time. And for any given star, it's measuring its brightness and its position or its timing of when it hits a particular position. Time and time and time again, as Gaia spins, that star will come around again, and it will take another set of measurements. And it will continue repeatedly taking those measurements to get the precision it needs. And because that star will come back some months later, then we'll get a timing of not only where the star is, we'll get the motion of that star through the sky. So Gaia is spinning. It actually spins once every 6 hours. The animations are speeded up so you can see what's going on. Remember, it takes a minute for the stars to drift across the detector. It takes 6 hours before those stars come back again in the same telescope. The two telescopes are pointing at different parts of the sky. So a star will appear in one telescope, and then a few hours later will appear in the other telescope, and the timing difference of those two appearances gives you the angle between those two stars extremely accurately. If you measure the timings to microsecond resolution, you get angles to phenomenal precision. The axis is precessing around the sun, which means as Gaia spins, it's mapping out a ribbon of sky, and as it precesses, that ribbon of sky sweeps over the entire sky. And this graphic in the bottom right gives you an idea of how often a particular patch of sky is covered by Gaia. So the colors here indicate how often a particular batch of stars have been imaged. So you can see it's not necessarily uniform because of the way it maps out a ribbon of sky and that ribbon slowly sweeps out the entire sky. But ultimately, all stars in the sky will get covered multiple times over the 10 years of Gaia's lifetime. So what data was actually acquired? The bottom line is it acquires timings and it acquires brightnesses and colors and spectra. The timings have to be converted into, well, where is the star then? Remember, it doesn't take images. So all of the timings, this star arrived on this microsecond of the clock, this star arrived at this microsecond of the clock, all of those timings have to be converted into where are the stars in the sky that's consistent with all of the timings as recorded by Gaia. It's a huge computational task, which is why the data wasn't released on day one, even though the data was acquired on day one. It took a while to actually release the first data. So it was operating back in 2014, 5-year mission. They decided to extend it. It ultimately ended up operating for about 10.5 years. Data releases were timed in the way of, well, it's going to take our computing guys, our analysis guys, a while to take all of this data and figure out what the positions of all of these stars are and convert it into proper motion and parallax, which gives us distance. So the data releases were timed over a period of time, 7 data releases. You might think they'd call them 1 to 7. No, they decided to call them 1, 2, E, 3, F, 4, 5. Data release 1 basically said, let's take the first year's data of Gaia, let's convert all the timings into measurements, and then we release the coordinates of millions of stars, generally the brighter ones, for which we've got plenty of good data with only a year's worth of measurements. Data release 2 took the first 2 years of data. Remember, the repeated measurements mean the more data you take, the more accurately you can pin down the brightness as well as the position and hence the parallax and hence the distance. So data release 2 back in 2018 produced the coordinates not of millions but of billions of stars. The scientists were then getting antsy for data release 3 because they knew that was on its way. So they decided to have an early release. They took the first 3 years of data and say, this is not fully analyzed, but here's a whole load of interesting data for you. The same billions of stars as in data release 2, but with higher precision because we're taking 3 years of data rather than 2 years of data. So that kept the scientists happy for a while. Then there was the full data release 3, which gave precision data for billions of stars and in addition, a few extra things. It also found millions of variable stars because remember, it's taking the brightness as well as the time at which it hit a particular chip. So they've now got intensity variations of all of these stars, some of which don't change intensity much, some which appear to go through cycles, so we definitely have variable stars. So we now have good data on millions of variable stars. It also found millions of galaxies. It wasn't looking for galaxies, but we knew it would find them because some galaxies are so remote they appear essentially as pinpoint, essentially stellar objects. Some of these are really useful because if these are quasars, and we know some of them are from other measurements on other telescopes, quasars are very bright but very remote galaxies. These are galaxies that are billions of light years away. And if you think of the motion of the Earth around the Sun, if you're a billion light years away, well, the motion of the Earth around the Sun is going to make no difference whatsoever. So these quasars at the other side of the observable universe have essentially zero parallax and zero proper motion. They are taking the job of the fixed stars. They're not stars, but effectively it's a backdrop of lots of pinpoints of light that we assume are simply not moving, because that is our definition. These are so far away, these are fixed objects in the sky. So we're using the Sun as a reference, and now we have a whole load of dots in the sky, which we are saying are fixed background points. We now have our absolute coordinate system. We now have 100 million spectra of stars, which means we can now do really detailed work on stellar evolution, because we know exactly what the Hertzsprung-Russell diagram looks like now, because we have spectra and we have information about hundreds of millions of stars. By accident, we've also picked out a few 100,000 solar system objects, for instance, probably asteroids. Some of them we knew about, some of them we didn't. It's worth keeping an eye on them. Thereafter, there was a focused product release, hence F. Here was a release of the first 5 years of data, again, slightly higher precision. But in particular, they said, can we refine our analysis? The analysis we've done so far is fantastic, but can we make the analysis any better? There are some patches of sky which are really, really crowded. And if we want to resolve individual stars and see how they're moving, can we do that even when they are closely packed together? For instance, what happens at the center of a globular cluster? This is Omega Centauri. Even the Hubble Space Telescope has difficulty trying to see individual stars in the middle of a globular cluster. So they tried to refine the analysis in Gaia to try and see not only what's happening to these stars out there, but can we figure out what's happening to these stars that are really close together, such that the pixels of one star are barely different from the pixels of another star. They wanted to do this not simply so they could understand globular clusters and other clusters better, but they wanted to be able to look as much as possible towards the center of our galaxy, or the center of the Large Magellanic Cloud, where we have a really crowded area of sky. So they're using Omega Centauri as a touchstone, as a test bed. Now they've refined their analysis, they hope that future data releases will give even higher precision than they are able to get up to this point. Data release 4 is coming. It'll be a few months yet. I think the currently slated date is December 2026 will be data release 4, and then a few years data release 5, which will include the entire 10-year data set. And that, again, will have simply higher precision than anything that's been released to date. What have we learned from the data releases we've had so far? This is currently what we think the Milky Way looks like based on Gaia data. We now have a very clear bar in the center of the Milky Way. That's us there in the Orion arm. I seem to remember it used to be the Orion spur, but apparently it's had a promotion. It's now the Orion arm of the Milky Way. The yellow dot indicates that we are about 8,000 parsecs from the center, or if you prefer in old money, 25,000 light years from the center. So that's our position. If we think about what Hipparchus was able to do in terms of how far did Hipparchus actually reach into the Milky Way in terms of local stars, well, all the stars that Hipparchus saw were inside that yellow dot. Those 100,000 stars are, in a sense, our immediate neighbors. Gaia, with ability to look at fainter stars and, remember, much higher precision on parallax means that we can work out the parallax of more distant stars. The intention was that we would be able to see further into the galaxy than Hipparchus could. Data release 2 took us out and allowed us to see more stars in the Milky Way. That was data release 2, 2018. We are now sampling parts of our own spiral arm, but not the next spiral arm. Data release 3 was a game changer because that opened up not simply millions, but billions of stars accurately so that we could determine their distances. And the reach of Gaia for data release 3 was phenomenal. It allowed us to get a really large chunk of the galaxy. I'm not saying that every star in that circle was measured, but basically it was able to look at stars within that green circle at the very distant edges, perhaps only the brightest of stars, but billions of stars within that green circle have now had their distances and their spectra and their colors, etc., measured. Gaia is still having a difficulty in this central region because it is so dense and so dusty there, it's difficult to see what's going on. So whenever you see this, you tend to think, that's a nice image produced by Gaia. Well, it's actually not an image. It's a map. And each pixel is basically not saying how bright are the stars in that part of the galaxy. Each pixel is how many stars did Gaia count in that particular chunk of sky. Was it 1,000 or 10,000 or 100,000 stars in that particular pixel? So each pixel is color-coded as to how many stars Gaia found. And when you produce a map that looks like that, it ends up looking like a map of the sky because, of course, there are lots of stars in the center of the Milky Way. The Milky Way is quite dusty, so there are some regions which don't have as many stars to count. And, of course, we also get lots of stars in the large and small Magellanic Clouds. So it looks like an image, but technically it isn't. What can we learn from all the data that's been coming out of Gaia? Well, I mentioned just a while ago that we now have distances and spectra and colors of not just a few, but a huge number of stars. Many millions of stars, hundreds of millions of stars, we now know their color and their luminosity because we know their distance. So up till this point, we guessed what the Hertzsprung-Russell diagram of a Milky Way looked like. Now we know what the Hertzsprung-Russell diagram looks like. This is not an artist's impression. Every dot is a star. A star we can pinpoint and say that star there is at that distance with that particular color. There are so many dots in the main sequence going down here. There are so many dots, they all pile together, and so we've simply color-coded how many dots are there in each pixel of this particular map. But effectively, that is now a Hertzsprung-Russell diagram of the Milky Way as we've mapped it out so far. So rather than just guessing, we now know what the HR diagram of the population around us looks like. And we can now start testing our ideas of what we think we understand about stellar evolution. Along the way, Gaia found a few surprises. It found lots of objects that appear to be sun-like stars that are orbiting, well, nothing in particular. Once we take out the effect of parallax, once we take out the effect of proper motion, some of those stars are still orbiting something we can't see, something that's not massive enough to be a black hole, but must be quite faint. It is thought that these are neutron stars, sun-like stars that are orbiting neutron stars, quite a few of them. It's not just an isolated one or two, dozens of them. How can that be? Neutron stars are born in supernova. How can a sun-like star be orbiting something that was born in a supernova? That doesn't seem to make sense. So again, the people who study stellar evolution are trying to work out how this can happen. It turns out the Milky Way is warped. It's not two fried eggs back to back, or it is if you like, but it's got a definite slight S shape to it. We've known other galaxies look like this particular galaxy, 4565. Perhaps it doesn't show up too well, but if you look very closely at the dust lane again is slightly S-shaped, indicating that this galaxy is slightly warped. We suspected that the Milky Way might also show a warp. Now we know it actually does by mapping out the positions of stars and determining what the three-dimensional structure is. Why do we think any galaxy might have a warped disk? Almost certainly because of interactions with other galaxies in the past. We can work out stellar motion. So here we've got a few random dots, and we can sort of play a movie of where the stars are actually going in terms of how they're moving relative to us. And you can see all of these streaks going all over the place. Some of them look to be in rather odd orbits. That's partly just a question of the projection. But because we can now decouple the distance to a star as well as the motion to a star, we can work out how stars are moving. Are all the stars that we can measure, all of these billions of stars, are they all going around the Milky Way as we would expect? Well, most of them are. But some of them are going backwards. Some of them are going over the top. Some of them are in very elongated orbits rather than simply in circular orbits all going perpendicular to the center of the Milky Way. Why should some stars in the Milky Way be going in very odd orbits? With a bit of detective work, we can say, well, it must be because these stars are the result of galaxy interactions. We've always assumed that the Milky Way is the result of lots of smaller galaxies either merging together or colliding, or maybe the Milky Way has been eating some smaller galaxies. We've always assumed that was the case by looking at other galaxies in the universe and seeing them interact with each other. So rather now just assuming that the galaxy has interacted with other galaxies in the past, by looking at the way stars are moving in the Milky Way, we now know that the Milky Way has interacted. This isn't a genuine family tree, this is just schematic. But we can now say, yes, the Milky Way has interacted with other smaller galaxies in the past, and we can map them out with some precision. So here's a timescale, Big Bang on the left, where we are now 14 billion years later, or if you prefer, that's now, and that's 14 billion years ago. We have interacted with a number of different smaller galaxies in the past. Some of these interactions go back way back more than 10 billion years, when the universe was fairly young, and some of them are still ongoing. I'm not going to talk through all of them, but for instance, Enceladus is a galaxy that's interacted with us, when was it? Between 8 and 11 billion years ago, or thereabouts. It looks like some of the globular clusters that are currently in the Milky Way came from the Enceladus galaxy. In other words, we've stolen their globular clusters. Some of the globular clusters in our galaxy seem to be of a population that doesn't quite match the others. Our globular clusters, if you like, come in multiple populations, and we think some of them were brought into our galaxy when we merged with the Enceladus galaxy many, many billions of years ago. But let me say something about this one, the Sagittarius dwarf galaxy. This interaction started some 6 billion years ago, and notice that it doesn't have an end. We think that interaction is still ongoing. This is what we think has happened based on how we see stars moving around the Milky Way because of Gaia data. We work, if you like, run the clock backwards and try and work out what must the interaction have been to give us the stars that we see today. And it looks like the Sagittarius dwarf galaxy clipped the Milky Way some 6 billion years ago, and whenever galaxies interact with each other, you get a whole load of new star formation. The star formation rate goes up. And then the galaxy came back and clipped us a second time some 2 billion years ago. And then the galaxy came back and clipped us a third time 1 billion years ago. Notice that it leaves a breadcrumb trail of stars behind it. These star streams, or if you like, tidal tails. Whenever you have two galaxies gravitationally interacting with each other, some galaxies will always be ripped out of one galaxy or the other, and you'll end up with these star streams. So these star streams, if you like, are the detective's way of telling what interactions have taken place. One of the intriguing things about the Sagittarius dwarf galaxy, so called because at the moment it happens to be sitting in the constellation of Sagittarius, that's why we hadn't noticed it until now, because it's, as it were, behind the center of the Milky Way. The center of the Milky Way is in the constellation of Sagittarius. The Sagittarius dwarf galaxy is just behind that, so it's very difficult to see, but Gaia has picked it out from the background stars. What's interesting is the fact that the first clip took place about 6 billion years ago. We know that whenever a galaxy interacts with us, we get new star formation. 6 billion years ago, just after 6 billion years ago, that's when our sun formed. So we can't prove it, but it might just be a coincidence. But it looks like the Earth and the Sun were born just after the Sagittarius dwarf galaxy clipped us. So it might be that we owe our existence to that particular dwarf galaxy, which happened to come quite close and nudge the Milky Way into producing a few more stars. Maybe ours was one of them. Star streams are nothing new. We've seen star streams in other galaxies. This one, NGC 5907, I hope you can see, but I'll invert it to make it even clearer. You can see these star streams indicating that this particular spiral galaxy has interacted with others in its past. Even galaxies that look relatively isolated, like Messier 63, for instance. If you invert it and bump the contrast up, it's fairly clear that there are star streams everywhere, indicating that a lot of galaxies have interacted in their past. If we do the same again, perhaps the star streams aren't as clear, but clearly there's an awful lot going on there, which indicates that galaxies have been interacting with each other. We've been seeing this for decades when we look at other galaxies. We assumed that our Milky Way was no different. Now we know that that's the case from Gaia data. Not only can we say what has happened in the past by looking at what are the pieces of evidence in the way stars are moving through the Milky Way, we can actually say something about what's going to happen in the future. Again, knowing how stars are moving now, we can say, well, if they're moving at this speed in this direction, what's going to happen in the next few billion years? And we know we're going to continue to interact with the Sagittarius dwarf galaxy for a little while yet. And we know there are two galaxy mergers on their way. One of them, we are going to merge with the Large Magellanic Cloud. That is almost inevitable. We can see how the stars in the LMC are moving, and we can work out what they're doing relative to the Milky Way. We are going to cannibalize the LMC at some point. We also have got a pretty good idea that we're going to merge with M31, the Andromeda Galaxy. Using Doppler, looking at the Doppler effect on stars using the redshift or the blue shift, in the case of Andromeda, a blue shift indicating that Andromeda is coming towards us. What's much more difficult is to work out whether it's moving to the left or the right in the sky. We know fairly precisely the speed at which it's coming towards us, but we don't know whether it's going to be a head-on collision or a glancing blow until we get the left-right motion sorted out, the proper motion. What is absolutely incredible is that Gaia, designed to look at the parallax of stars that are hundreds or thousands of light years away, is just about capable of measuring the parallax of a star in the Andromeda Galaxy at 2.5 million light years. That's a ridiculously small parallax, and hopefully when we have the full set of 10 years of data, when data release 5 is released, we should be able to get the parallax of individual stars in the M31 galaxy. Then we'll be able to tell how it's moving, and with the Doppler shift, the blue shift telling us the speed at which it's coming towards us, we'll be able to work out what that collision is going to be looking like, what sort of merger we can expect in 4 or so billion years' time. Let me finish with a short epilogue. The data from Gaia, the acquisition finished early last year, in January 2025. Remember, it was orbiting around L2 for its 10.5-year lifetime. Once it had finished, they wanted it out of L2 because L2 is getting very busy. James Webb Space Telescope, the Nancy Grace Romans telescope, hopefully to be launched next month, will be going to the same place. So they wanted Gaia out of the way. How do you move a telescope like that out of the way? All you need to do is to give it the smallest of nudge away from L2. L2 is a stable or metastable point. In other words, a spacecraft will sit at L2 quite happily. As soon as you push it away from L2, it goes into a so-called retirement orbit. So much better than a graveyard orbit, I thought. A retirement orbit, so it can peacefully move away from L2. It will no longer go around the sun at the same speed as the Earth, which is what L2 is all about. All of the Lagrange points are moving around the sun at the same speed, the same rotation rate, 1 revolution per year. All of the Lagrange points are rotating around, but because Gaia is now a little bit further away than L2, it's now moving around the Sun in an independent orbit, so it's no longer going to be getting in the way of anything else that's around L2. It'll take quite a few years for it eventually to go around the Sun, and it might come back close to Earth, but not close enough to cause any problem with any other telescopes. As it drifted away from L2, some amateurs actually managed to pick up there's an S-shaped curve of Gaia moving away from the L2 point in the sky. It's thought that it might be back in another 14 years or so, maybe not close enough to be bright enough to photograph again, and again, it'll be nowhere near any other telescopes of the time. Just before they powered it down, the mission controllers, had a last transmission from Gaia, which was basically, if you look at the structure, they deliberately sent it a whole load of numbers such that when they color-coded the numbers, it came back with a goodbye message. Nancy Grace Roman goes up in a little while. It's not a replacement for Gaia. Some people have asked, will Gaia ever be replaced? It's done some fantastic work, and we're still analyzing Gaia data. Will there ever be a Gaia version 2? Well, Nancy Grace Roman is not Gaia 2. But Nancy Grace Roman will have some phenomenal precision. That in the center there is the Pillars of Creation. This is the Eagle Nebula. That's the Pillars of Creation as imaged by Hubble. The Nancy Grace Roman detector has got the same resolution as Hubble, but the detector is 100 times the area, as you can see from this particular graphic. So NGR will be able to image a huge chunk of sky to the same resolution as Hubble. And because it's infrared, it'll be able to look at some of the dustier parts of our galaxy. So it will be tasked at some point to look for stars towards the center of our galaxy, and it might be able to produce parallax measurements of some of those most distant stars to improve on some of the Gaia data. But Nancy Grace Roman has got a lot of things to do. It'll only be spending part of its time on that particular task. Gaia is going to be producing a lot of data in Data Release 4. It's estimated that Data Release 4, which is coming in December of this year, will be perhaps 500 terabytes of data. And it's going to take a while for a lot of astrophysicists to pore over that data. I'm sure they're going to use some AI tools to help them, because otherwise 500 terabytes is simply too much to digest. Remember, that's a whole load of three-dimensional coordinates and velocities, proper motions, colors, spectra, etc. But Gaia has been summarized in two words: obscurity and ubiquity. Obscurity because it's nowhere near as famous as its cousins, the Hubble Space Telescope and the James Webb Space Telescope. That's because it produces measurements, not pretty images. So obscurity because a lot of people don't really understand what it has done. But ubiquity because Gaia data is everywhere. Gaia data is being used already, even before the final data releases. Gaia data is being used by every ground-based telescope. It's being used by every space telescope. It's being used by probably most, if not all, astrophysics research projects for the next decade, or 2 decades, maybe even 3 decades. The data that we've been getting so far, and the data that the scientists are already pouring through, have told us about Milky Way dynamics. By looking at the way stars are moving, we've got a much better idea of our home galaxy. And because we've also got star colors and star spectra, we've got a lot more information about stellar evolution. Along the way, by accident, we've also picked up information about neutron stars. Gaia has found some black holes. We found some solar system objects. We've also found some exoplanets by looking at the way some stars are moving, apparently wobbling because exoplanets are orbiting around them. By the time Data Release 5 comes along, the data will be precise enough and we'll have a large enough number of stars to look at that we might be able to start making some inroads in saying, well, according to all of these motions of all of these stars, can we figure out where all the dark matter is? And can we figure out what dark energy is doing? Gaia data is producing way more than simply star positions. It's feeding into astrophysics in just about all corners of astronomy and astrophysics. Gaia data is Gaia's legacy. Thank you all very much.